So the homework 3 will be due Friday. I'll be in my office hour today till 4 p.m. But I have I've got to be an online meeting, 12 to 12:30. But otherwise, feel free to stop by multiple times if you need. So all right, last time. All right, to review, so we've been doing these Rayleigh problems, right? We finished the Rayleigh problem, which was basically a plate going to the right at constant velocity, and we saw that there's basically a velocity field that formed at a distance from the plate that depend on time. Short times you get some motion near the plate, and then as you go farther and farther away, you get more motion. Now we extended that approach, so the governing equation for that was the following here. Because we had the velocity in the x direction, that was a function of the distance from the plate, which is y. Okay, and the time dependencies are the fact that the plate was not moving at time 0 and it become moving, and so there's some information on the time that goes in the problem. And so last time we had started this, we had started discussing this problem, how to do the oscillating version of this, and we said we got these two boundary conditions. Hey, that if I go really far away, I should have 0 velocity. But at the plate, I've got this no slip. That basically I have this oscillating velocity field with a magnitude u0. So it's basically going back and forth with a frequency omega. Okay. And I said, hey, because we have getting this cosine function here, the way people solve it, they don't use cosines. They use this Euler notation, where I'm saying, hey, u0 times, basically I'm going to write this as the real part of this thing, where e to I omega t is equal to cosine omega t plus I sine omega t. But the I part's just going to go along with the ride, and depending on the derivative, it may take part. Okay, and I said, well, if the forcing is going to go as this Euler function omega t, then my solution should also go like that. But I'm also having this solution in this form that I take this oscillatory term, and I'm going to multiply it by some function of y. This is in some ways kind of like a separation of variables. Before we did that, so in general, before we had u as a function of y comma t, it could be any weird convoluted thing. But I'm saying, hey, I expect it to be a product like this, so that the variables are separated. They're still together, but one's a function of t and the other one's a function of y. And then basically, now the problem is that so this is an easier problem than we did with the Rayleigh problem, because we didn't have to actually go to the similarity solution. Here I could basically just substitute it in. So the next step, once you propose a form of the solution, and this goes for the Rayleigh problem in your homework, you have to take derivatives of it so that you can actually substitute in the original PD. And so that's what we did. We substituted for time, and we substituted for velocity, for distance squared, taking with respect to y squared. And because of the separation, basically I have this f double dot, and I have this one. And when I substitute back in, everything canceled out except for this new information about f. This is also a very common way to go forward. You're going to write a solution set, and then you're going to get a new equation that is now an ODE. So we went from PDE to ODE with basically this basically describing it as this U as a product. Okay, and this ODE, ordinary differential equation, it just says the second derivative of f is proportional to f. So this is a proportionality constant, and that we know all solutions that satisfy this are going to look like exponentials. Well, all we had to do was take the square root of a constant times I. Okay, and that's what I did here for you. I said, hey, we have this complex plane where you have the real numbers on this thing and the imaginary numbers here. So how do I get the square root of I? Well, I basically said, hey, e to the I theta is basically e to the I pi over 2, that's basically my I, because you have no real part, you only have an imaginary part. E to the I pi over 2, we call that I. If I take the square root of that, basically that is e to the I pi over 4 by our exponential rules, and that's just square root of I. So it went from original point was here, and the square root of that was here. And that's how I figured out what the exponential term in my solution should look like. It should like 1 plus I over square root of 2. Okay. All right, so this was actually quite easy compared to the other problem we did in class. Now that we have our solution set, it looks like this, and then we substitute back in. We just solved for what the exponential should be. You know, this is just a constant. That's square root of this omega over nu. And we basically substitute back in, and we got this. And we took the real part, so we don't have to deal with the imaginary part anymore. And so we have basically, you have something that decays with distance. So I kind of drew it in the beginning of class last time, but I didn't defend it. That's asking too much from the screen. But basically, very, very far away from it, it kind of decreases in amplitude, but it's oscillatory throughout. So what I'm drawing here is like a snapshot in time of what the solution looks like. Okay. All right. All right. So for the last problem on the homework, you need to calculate a couple different quantities, and we started by talking about dissipation phi. And dissipation phi, when you did your homework for the bathtub problem, that it took like 30 days to heat up your bath water.
Almost double
You were probably heating up your brain actually creates a lot of heat too. You probably could have heated up your bath water by just trying to solve that. It probably may take more time. But brains are still actually way more efficient than computers somehow. I think you use like 20 to 40% of your energy in your brain, depending on like how active you are. Like these chess players, they're eating like 5,000 calories a day, and they're losing like 5 pounds for each tournament. All right, so for the bathtub problem, du dy was a constant, right? Because you had a Couette flow, so that was just a constant. But here, you got to substitute it in. And I told you a trick that basically, if you want to figure out the time average of these quantities, you basically have to write you write A as this quantity, B as this thing, and then you basically take the real part of this product. A naught times B naught to the complex conjugate. So let's use that, and the 1/2. All right. Oops. All right, the 1/2 we won't, and you can look up this online. This is on not Wikipedia but Wolfram. But it's really just algebra that you multiply these factors together, and basically some things cancel out. But this 1/2 comes from the fact that integral of cosine squared omega t dt over 1 cycle is 1/2. Okay, and the reason why that's 1/2 is because if you integrate cosine squared omega t plus sine squared omega t, that's this dt, that's just equal to 1 over 1 cycle, because that's the integral of 1 dt. So that just gives you 1. So the reason 1 is 1/2 because cosine and sine squared look identical across the cycle. At least their integrals do. All right. So let's apply that to actually for this particular problem. The dissipation rate. D. So that's the time average of the dissipation. We got mu. So if you use this method that I showed you, you have 1/2, and you were to here. Let's just write du dy because that's what we had last time, dv. All right. So remember we have u. We written it on the board last time, and so if you take the derivative, you're going to get so remember u was the real part of u naught e to the I omega t f of y. All right, and so basically if you take du dy, you're going to get f primes. So d using the trick that we showed you last time, the integral of this thing squared, I'm going to substitute basically a and b to be the same thing. So you're going to get 1/2 u naught f prime for the first term. In the second term, you get f prime star, okay, dv. And then because f is a function, has stuff in the exponential, if you multiply the stuff that comes out together, you should get this. And you have trouble working it out, we can work it out on the board. Squared. All right, so now we substitute for f here, so we can actually evaluate this thing. And you're going to evaluate it across your whole volume, y equals 0. You have that oscillating plate, so it's from the plate to infinity, and you have decreasing contributions as you go far away to omega over nu y dv omega over nu. And if you multiply these out, you should get 1/2 mu u naught squared nu over 2 omega times omega over nu. And then this simplifies to, let's put down here, it's 1/2 mu u naught squared. Okay. So that's the final answer for, okay, dissipation rate. So basically that's the, energy per time that's, imagine physically what's going on. If I have like a vat of molasses and I'm shaking the bottom, how much energy is being dissipated in the fluid. And the reason why energy is being dissipated in the fluid is that there's a strain. There's a rate of strain. So anytime I've got basically a velocity that's changing with y, fluid's shearing, and it doesn't like to do that. And the amount of shearing is going to be proportional to this viscosity, velocity squared, because I've got a velocity in here, and this actually becomes really elegant because of the way the solution is. So that's the amount of energy per time that's being dissipated. Physically, what's going on? That is going on because I'm putting energy into the system, and let's show that. And that's what you're going to be doing for the homework for the wine tiers. The rate energy that's going in is being done by at the boundary. So the rate of work done by lower boundary I'll call that W. The undergrads got mad at me because I made my omegas look like W's. All right, so make it W. Mu du dy. And these should be technically these should be partial derivatives because you use a function y and t. But if you write it as non-partial, you're still going to probably calculate it the same way. All right. So the rate of work done at the boundary, basically I've got my stress. So this is my stress times my speed. Why is that? Because so it should go like energy is basically so this would be force over area times length over time. Force by length is going to give you energy, and you're dividing by here. So rate of work done by boundary per unit area of boundary. Okay, so that's the exact thing that we're calculating here, because the bottom plate it's infinite plate in both directions. So the best I can do is calculate it per unit area. All right, and this bracket means time average, and using the same idea from above, that's basically going to be the real part of 1/2 u naught mu u naught omega over 2 nu 1 plus I. That's equal to 1/2 mu u naught squared over omega over 2 nu. Okay, And remember, I calculated this through a totally independent way. I just looked at what was the velocity at the boundary, because the velocity tells me how much work per unit time I'm doing. I looked at the force on the boundary, force per unit area. And I multiplied those together, and I got basically the same amount as the dissipation of the fluid. So you should, basically from this physically, you should know in this problem, any work I'm doing in the boundary is being dissipated by the fluid instantaneously. And what I've calculated is the time average work, as I go through a cycle, how much energy per cycle that's going on. And physically, this should make sense. The energy is not accumulating in the system. This is like is constantly being dissipated. Imagine this thing has been going on for all time, like very, very far away. It's really moving a little bit, but basically all the energy is like kind of like going away as I'm putting it in. It's kind of like a steady state problem. Okay. So what we've done are called exact solutions. Navier-Stokes, there's not too many. If you find a new one that's useful to people, you can probably publish a Journal of Fluid Mechanics paper. So we solved the bottom plate moving. You could also solve this. I don't know, this might be useful for your research. You can also solve this for the case of basically, you could have the shear stress or a velocity on the bottom greater than 0 for time is greater than 0. You could have a bottom plate moving when the top plate is fixed. That's kind of like a flow between two plates. You could have same situation except the bottom plate is oscillating. So you could have basically, and it could be oscillating a velocity field like we showed, or oscillating shear stress, cosine omega t. You could have flow through, we showed the solution for a circular channel, but you could have a what's called rectangular pipe flow. And this method that I'm going to use, G of t, remember, was the pressure as a function of time. You can show this to be the case. You can show that you can use these methods to get solutions for these. What we're going to do next is the following problem with a cylindrical geometry. Cylinders have been really, really useful in engineering because they kind of provide, they're kind of easy to fabricate. Their stresses are kind of nice to calculate. And they have the minimum surface area per unit volume. So, for example, this one, which we're going to do, I think you do a version of this for the homework. Basically, you've got some spinning omega. You could also have a simultaneous like velocity and velocity going through here. And these lead to what's called Bessel functions. The one we did in class led to the error function. Bessel function is another solution to our differential equation. And we're not going to do this, but spherical geometries use spherical coordinates. But those, I think there's one, Io, is Io here? There's this guy named Io, not here today, but he I think he's Earth planetary sciences. So if you're trying to study like the motion of the Earth's core and stuff like that, you'll want a spherical geometry. And then the solution, that looks like Legendre polynomials. All right. Okay, so let's, I have one more problem to do before you can do every single problem in the homework. and let's flow in a circular tube. So let's do that together. And then we'll spend some time. I'm going to pass out the new homework, and we'll spend some time. This lecture, we probably won't get to too much, but definitely next lecture, getting your last questions on the last questions on the homework before it's due. I will probably choose the quiz on one of these different geometries that I talked about, but I haven't decided yet. All right, so we got this, basically a situation like this. We're going to assume that is at rest, and then we're going to apply some pressure field and see how it builds up. So remember, we call this Z. We call this R, and this we're going to have a length scale R naught that sets a lot of the physics. Field evolve to a steady parabolic. So Poisson profile. All right, so what we learned before, that the steady state solution, I think I'm gonna notate this as USS, U steady state. The velocity field looks like this. G over 4 mu R naught squared minus R squared. All right, we solved for that a couple lectures ago, where you got this pressure gradient, G pressure gradient. All right. And we know what the steady state solution looks like. Now we're going to solve how it evolves to that from rest. And just to tell you what it looks like, it's going to look like this. We're going to show how we can get that. So basically, we're going to, the big picture is that we're going to write this as a sum of the steady state solution and a time-dependent part. We're going to substitute that into the Navier-Stokes z-hat direction momentum equation, and then we're going to get a new equation for the non-steady state part that we're going to solve for. So in some ways, we're figuring out like the unsteady part that this is the equilibrium, and we're trying to figure out what unsteady part gets to that equilibrium. All right. So physically, why does that? How does physically what's going on? So we expect diffusion of vorticity from the walls. Remember, just like the last two problems, so the last two problems were plates, infinite plates, and we were really, really far away. And you said if you're far enough away, you don't even know the plate's moving. Similarly, if you're right in the center of the channel, it'll take you time for the information to get there. And that time is going to start at the walls and go towards the center. You're right in the last two problems, the walls were moving, but they provide information of what the flow should be. In this case, you're having a pressure through the center, through the whole thing, but the walls tell you that that part kind of like hold you back. So it's like the walls are still moving, but they're moving backward. I don't know if that was a good explanation, but like the flow wants to go forward, the walls are holding you back. Yeah. Oh, that's Z. That's yeah. This is R naught. Yeah. No. Yeah. Sorry, all right. There we go. It's just that's the length scale. You can also think of physically what's going on is a thickening of the viscous boundary layer. The boundary layer tells you like when the velocity is close to zero. I think it's like 95% of the mean of the maximum velocity. And basically in the beginning, it's really, really thin, and then it gets thicker and thicker as the information flow walls goes through. So thickening of viscous, there's no quotes there. Thickening of viscous boundary layer until entire flow field is influenced by the walls. Okay, so that's kind of physically what we expect, and this problem is useful for blood flow because nature's decided that, hey, we want to use the minimum amount of material too, because you don't want to carry around like too much weight, so we're going to have round blood vessels. But there's also, if you ever have volcanoes, those lava tunnels have also become circular because they've eaten away, and that's what's equilibrium. So this circular tubes appear in nature like all the time. All right, so in all these problems that we're given, there's a direction that is kind of like infinite in that direction. So that means that's going to be a key. In this case, there's only one direction that's infinite. It's finite in the r directions. But basically, we're going to assume that the velocity field only goes in the z direction. So there's no flow towards the walls. It's always going parallel to the walls. Okay. We're going to call this u. Okay. In other words, we're assuming that u theta equals 0 and u r is 0. So no flow towards the walls, and this is also axisymmetric. This is going to be a big assumption you use everywhere, that because it's axisymmetric, you don't expect to be any spin. So, our three Navier-Stokes three linear equations, nonlinear equations, become one nonlinear equation. So probably you can print out Navier-Stokes in cylindrical or Cartesian. You'll find on Wikipedia or something. But the z-hat momentum, I can remember the Cartesian one, but I can't remember the cylindrical one. So the z-hat component of the momentum equation in cylindrical coordinates. Of course, if I give you this on a quiz, I will give you the momentum equations. With those assumptions that we wrote up there, that those two directions of velocity are 0, and I've decided, hey, since I only care about the z velocity, I'm not going to write uz over and over again. I'm just going to call that u. We have the following left. d by dr of r du dr. The nested derivatives. This is our governing equation for the system. I'm going to box it, and we're going to call it star. This is the governing equation. That's going to dictate how we're going to, this is a PDE. Remember, left side is a function of time, the right side is a function of space. We're going to use that to turn into an ODE and solve. So that's the governing equation. Next thing, we got to write the boundary conditions. So the initial condition is that we're basically at rest. All right, so this is the equation of u as a function of r comma t. Okay, so u r comma 0 is the initial condition. Basically, u at all space at time equals 0, that's going to equal to 0. Okay, so basically it's stationary in the beginning. And my boundary conditions are that basically at the wall, I don't got any slip. And that I want one stay bounded, because A lot of you, maybe if you remember when you solved the z-hat momentum equation, there was a log term when you solve that, and we don't want that because it's going to be like bad things going to happen at r equals 0. So this is basically at the center, in particular at center of the tube. That's where bad things happen. Okay. So problem 1 in the homework, you practice doing Buckingham's theorem. Or if you haven't do it, you'll be practicing Thursday late night, but I hope you don't practice that late. You practice Buckingham's theorem, and then you also non-dimensionalize the governing equations. For problem 2 on the homework and 3, definitely problem 2, it's useful to basically non-dimensionalize the beginning because you carry around less stuff. You could do it at the end, but it's more writing. And why would we non-dimensionalize? Look at this governing equation. It's got two things that I don't really want to write over and over again. The g and the mu. Those are constants. Those are given in the system. And if I non-dimensionalize it in a smart way, I could basically not write those things, and those could just be ones, which would be really nice for me. So I want to get rid of those two factors and not write those over and again, and I could just use dimensionless units. Oh, I also got the row. I got 3 things in there that I want to get rid of. So that's my plea to non-dimensionalize. The other reason you non-dimensionalize, it gives you some idea of physically what you expect your solution to look like. You're not just going like a hero in the dark. You actually have some ammo. So non-dimensionalize. So we're going to choose a length scale. What do you think the length scale should be? Yeah. That's the only. In fact, that's the only possibility because it's infinitely long. All right. The velocity scale. All right. Let's for the velocity scale. Let's look at what the steady state solution looks like. Let's just box this too, because we kind of this is the only thing we know about the problem. If I were to guess a velocity scale, what would it look like? Yeah, exactly right. So if you have no other ammo, someone you were taking a quiz and I gave you a piece of paper the size of a postage stamp, I'm asking what's the velocity? This already has the units of velocity in it because it's basically the pressure dp dz divided by mu times r naught. So, and that's what Cedric said, little r is equal to 0. So that's what I'm going to choose. I'm going to use the physics of the steady state solution to dictate what my velocity field should be. And I think without solving, a good quiz problem would be, I would say, hey, figure that out from dimensional analysis, because you could also figure that out from dimensional analysis too. So, and now that I've got my length scale and my velocity scale, I can easily get my time scale, which can be the, I want to keep it simple. So I'm going to do r squared over nu, all right? And this is what we've seen many times before. This is the diffusion time scale. How long stuff, basically, if you're at a distance r naught away, how long it takes information to to go a distance r naught, if you have a fluid viscosity, dynamic viscosity nu. Okay. And this r naught over nu is appeared many, many times. I think it appeared. It appeared in. It appered in our, remember our similarity variable back for the other problem? We had eta was y over square root of c of nu t. That's where it came. And we kind of had a little bit of a version in the oscillating plate example, where your exponentials had basically a time scale and a nu and a length scale. So if you memorize anything, you kind of try to keep this in mind. And this comes from just the bare fact that nu has the units of length scale, length squared over time. Remember, they call that they call that kinematic viscosity. Kinematic. because the Reynolds number tells us that, weirdly enough, to figure out like what the fluid flows look like, you just need to know the kinematics. You don't have to know anything about forces. You just need to know lengths and times. All right, so now we're armed with our 3 units here. Let's use that to non-dimensionalize. So just for kicks, let's not use the star. Let's use the bars. We're allowed to have fun in this class. U bar. I give you guys permission to have fun. So I'm divided by these 3 length scales. UC. Sorry, let me not skip steps. It's really confusing people. We'll call this LC. LC. And T bar is equal to T over TC. All right, and substituting with all that stuff I have up there. I'm just going... Do we want to take time and substitute in, or can I assume that people can do this by now? Who wants to do it together to substitute these 3 in? Or who? Raise your hand if you're definitely okay with it. All right, then raise your hand if you want to substitute it in. Just do it?
Yeah, do it for me.
Do it for, okay. Do it for, I'm not, yeah, if you, there's, okay, all right, let's substitute it in. All right, so let's just rewrite that big equation. And let's all do it at our seats, okay? All right, so we got, all right, the first thing is probably the easiest for you, that's the definitions of these variables, but what I am actually going to substitute it in, I'm going to substitute the dimensional ones, right? So I'm going to write it like this. T is equal to TC, T bar, okay? All right, and yeah?
Another choice of velocity scale could be just length scale or time scale. R naught upon...
Yeah, good point. But physically, what I'm trying to do is get rid of like the G. I want to get rid of, my goal for the dimensional analysis is to not make my problem more complicated. I want to get rid of stuff so I can not write stuff. So I want to get rid of the G, so I want to incorporate that somewhere. But you're right, it would have been simpler to do otherwise. But I'm trying to get rid of rho, G, and mu. Yeah. All right. So I write it like this, and to make it even easier, I'm just going to write out the stuff. So that R is equal to that, U is equal to G R naught squared over mu, U bar, and T is equal to R naught squared over nu, T bar. Okay, now I can substitute stuff in. And because I want to write my dimensional stuff in terms of my dimensionless stuff, if I substitute that in, I'll get a new equation in my dimensionless stuff, right? So rho du dt is equal to G plus mu over R d by dr, R du dr. All right, that's the governing equation, right? Dimensional equation. And I want to turn that to dimensionless. So I got to substitute all these 3 things in there. So why don't you see if you can do that at your seat. And then we'll... So every time I see a U, I substitute that expression for U bar with the, the constants in front. Every time I see a T, I'm going to do that. And then let's crank it through. Oh, did I mess it up?
I'm just looking at what you've got for U.
G R naught squared over mu.
Gotcha.
Now I'm going to do my creepy walking around. I'm sure people are not watching like World Cup or something. And if you're like totally lost, raise your hand, I'll come over. And you can use this idea that nu is equal to mu over rho. Or this is star. So subbing these length scale, you should get the following. R G naught. All right, if I were to do this really slowly, it would go like this. Du bar, so the u bar, substitute in, I get this factor in the front, right? And then dt bar, I get this other factor, nu over rho naught squared, right? So I only get two factors up front on the left-hand side. That's quite easy. And then I copy the rest, g plus. Now here, you think about it, I've got an r in the numerator and then two r's in the denominator. So, and I've also got this u. So basically, all together, that should give you the following. G plus g r naught squared over mu, 1 over r naught squared. And then everything should be barred. D by dr bar, r bar, du bar, dr bar. All right. And if you do your algebra correctly, you should get something as something has gotten better. Your new equation should look like this. All right. This equation is improved in two ways. It doesn't have the rho, it doesn't have the g with three ways, and it doesn't have the mu. We can just have ones for those. So this is going to be, this is my dimensionless PD, and we're going to call this x. Equation. And one thing you notice, I mean, this was true before. All right. Those of you who've taken heat transfer before, you've probably done a lot of separation of variables, but it can only be possible if you have a homogeneous PDE. You're non-homogeneous when you have any constant term, because it just messes up. You can't just like assume that's a product of stuff because it doesn't divide out nice. So this non-homogeneous PDE, and also, in other words, that u equals 0 is not a solution, right? Because you're going to have 0 on the left, and then on the right you'll have 1. All right, so that means we cannot just do separation of variables right now. We have to basically write in terms of, we have to figure out what write in terms of, so the goal is, let's see, we're going to do a time-dependent problem. We're going to seek a solution that's going to be u bar of r bar and t bar is equal to basically what's called the steady state solution, which we talked about it earlier, but we're going to have to write it in our dimensionless form, and our time-dependent solution. Okay, so this is steady state. You notice the steady state solution does not have dependence on time, because that was the whole, it's steady state, it's there forever, and this is the time-dependent solution. All right, so I'm almost ready to proceed, except I need to figure out, my steady state solution before was in dimensional units, so I want to figure out in dimensionless units. U bar SS as a function of R satisfies. Remember our new PD in dimensional, if it's time dependent, if it's a steady state, the left-hand side is 0. So it satisfies the following. 0 is equal to 1 plus 1 over R bar d dr of R du dr. Yep. So it satisfies that. So you could do the steady state solution in two ways. One, we can integrate this twice and solve, or you can take our old solution that we had at the very beginning and non-dimensionalize that. But this is probably the more cleaner way because it uses the governing equation. So you integrate twice using the boundary conditions. So du steady state dr. That basically it looks like a bowl, so that the gradient of velocity is 0 at the center. That's basically what this says. And the velocity at the edge is no slip. The other thing about using dimensionless units, our position, like our edge of the tube, is not some arbitrary r naught. It's just 1. So this is this is at center. This means it's bowl-shaped velocity, and this is no slip. Okay, and I'll tell you that if you do that, you do integrate twice. It's going to look like this. So that original solution I wrote looks like this in the dimensionless world that we're in. 1/4 1 minus r squared. And you could redimensionalize. To get what we had before. US of r was a g over 4 mu times r naught squared minus little r squared. Okay. So now we're working in the dimensionless world. We have a lot less. We should not have no physical constants. If you have a physical constant, it means you had some algebraic issue, and and things have become greatly simplified. So that's a steady state solution. But now we got to figure out the non-steady state solution. So we're going to so this is the steady state solution. Now we do consider omega r of t. So to figure out the PD that satisfies this one, we substitute sub u bar into the equation x that we had in the previous slide, the dimensionless equation, right? Dimensionless version of our governing equation. And if you do that, remember the steady state solution is going to cancel out I'll just do it for you. You're going to get no time-dependent part on the left. If you do that, you should get this. dw dt is equal to 1 plus 1 over r d by dr. All right, so we're going to substitute this in. So you're going to du ss over dt. Sorry, dr. And then I got the other one. 1 over r bar d by dr bar r bar d w dr bar.
Is it W, not
It's
we're talking omegas.
it's supposed to be all W's. I try to use omega for rotational stuff,
Right.
but sometimes I forget. But they're all supposed to be this W, this time-dependent part. All right. So we're going to call this equation dot. Oops. All right, so the initial conditions for W. What do you think the initial, so we know what the initial condition for the whole thing was, that the whole velocity was 0. So what do you think the initial condition for W should be to make the whole velocity be 0 at the beginning? If W were 0, then the problem is that the U would be moving at the beginning. But USS is a steady state. So what we need to do at the beginning, we have to cancel out the steady state solution. So we're going to have negative 1/4 the steady state solution to make sure that, so W represents the transient. At infinite time, that W does not have, is disappeared. But at time equals 0 is basically what we need to make the solution look like it's quiescent. Now the boundary condition, we've got two boundary conditions. Remember, our position 1 now denotes the edge. So W of 1 of t, basically want to have no velocity of the wall. So this is for all t. And 2, we need W to be bounded again at r is equal to 0. Okay.
I'm going to ask a dumb question, but I have to.
Oh, go ahead.
What do you mean by bounded?
Bounded just means not like infinite. Like I can't have like a log of 0, and I can't have 1 over like an r there. So no w equals log r, and no w equals 1 over r. Okay. So I substitute in, and I can make one more simplification. So this term, because that's our steady solution, that's equal to 0, right? That's how we define the steady state solution. So that means I have a new equation where it's homogeneous. So now our new PDE for W is homogeneous. That means W equals 0 is a solution. And that means I can use my separation of variables. Which is the first time you're doing it here, but you've probably, raise your hand if you did separation of variables before in heat transfer or any undergrad. Okay, separation of variables. So that means we're going to assume, all right, let's separate variables. We kind of did in the last problem, but let's review again. We're going to say W is going to be a product. So in general, it's going to be some convoluted function where they're coupled. But here we're saying, hey, the solutions can be written as a product. It's like basically, you still got a lot of possible solutions. As we'll see, we're going to get an infinite number of solutions that we're going to have to add together. But it says at least they follow this form. And these are generally for homogeneous PDEs because you got derivatives of t on the left and then derivatives of r on the right. Okay. Sub into dot. So you sub that into dot. You can basically you can imagine I'm going to get everything. I'm going to get derivatives of t on the left and then get derivatives of r on the right. And I'm going to divide by the factor r, capital T. So I'm going to get this. 1 over r over 1 over little r of r bar dr bar. All right. So that's what we do with the separation of variables. So you sub into the star and divide by, I'll just tell you explicit instructions. Divide by RT. And then you're going to get, I promise you'll get this. Now, this is nice because the left-hand side is a function of t, function of time, and this is a function of space, of r bar. So the only way they could actually be equal to, because time and space are independent things, is if those are equal to a constant. And for physical reasons, we're going to call that constant negative. Why is that? If lambda squared, let's say lambda squared were negative, lambda squared less than 0 leads to things blowing up in time. E to the AT with a greater than 0. And remember, this is we're trying to figure out how long it takes to go to Poisson flow. And if it basically gets to like infinite velocity before it gets to Poisson flow, that's bad. So we can't have lambda squared less than 0. And lambda squared equals to 0 leads to T of t, the basically no transient into a constant, right? And that's not interesting either because the whole point of this was to figure out this transient function. So we're left with the only possible solution is we need to have a negative lambda squared. So we call it lambda squared just because we know that it's a negative value. The net thing is negative. Yeah?
For the first note, when you say that lambda squared is less than 0, do you mean lambda squared is greater than 0? Because then we'd have our negative lambda squared? Or am I misinterpreting that?
I mean that the right-hand side of this equation would be positive.
Okay.
Yeah, so if lambda were like some complex thing, like square root of like I or something like that, yeah, then lambda squared would be less than 0, and this would lead to an exponential solution.
Okay.
Yeah, yeah. Yeah, that's not the greatest way to say it, but basically we're left with this idea that it has to be negative. This right-hand side has to be a negative value. So it needs to be negative. And so that's basically what that says. All right, so now here's the issue. Separation of variables has led us to make progress. And we went from, so the roadmap is the big roadmap, we start with a dimensional PD. We made to a dimensionless PD. Then we came up with two solutions, a steady state solution and a transient solution. And we substitute those and we said, hey, if I substitute the steady state solution, I get a homogeneous PD. Now I've said my basically transient solution is a product of these two things. I get an ODE, basically, that I can solve. And each of these ODEs has a constant on the right. Now the issue is that constant has many, many different solutions. And I basically have to figure out what those solutions are using the equation for capital R. So the equation for capital T just tells you what the time-dependent part looks like. And this is kind of what you might have envisioned. If you solve for T of T, you have T of T bar is equal to e to the negative lambda squared T bar. Okay. That's basically saying it's going to exponentially approach the steady state solution. Now we solve for R bar. Okay. Now I've got this differential equation. So d squared r over dr squared plus 1 over r bar dr over dr bar plus lambda squared r is equal to 0. Where I've multiplied out the stuff out inside the parentheses. Okay. All right. This, we can rewrite this by multiplying by r bar squared dr bar plus lambda squared This is basically as far as you'll go, because this is called Bessel's equation. If you see basically this appearing in your homework or something like that, this is basically like, when they figure out sine and cosine, they were originally said those are just cosine and sine functions, and they're basically you would look them up. They basically are the solution to this equation, and they just see it so often that they call it, this is Bessel equation of order 0, where the order is basically in the following. So recall. Bessel's equation, I think it shows up a lot in other fields too, like acoustics maybe?
I haven't seen it yet. But
Okay, or maybe not acoustics, or heat transfer. Do you see what solution is that? Like for heat transfer, like a pipe or something, or?
I think it's through cylinder.
Yeah. And physically, the reason why is this thing showing up over and over again is because heat transfer of a pipe, that's like diffusion of heat. Here we're diffusing vorticity, or diffusing basically kind of like flow. We're moving information from the walls inward, and that takes time. The Bessel equation of order n looks like this: x squared d squared f dx squared plus x df dx plus lambda squared x squared minus n squared is equal to f is equal to 0. Where n is the order, and lambda is the eigenvalue. All right, so to basically apply Bessel's solutions, we're going to let S is equal to lambda R bar. And then we're going to have the equation S squared equals D squared. Then basically, if we set S equal to lambda R bar, then our original equation, I'm kind of running out of symbols. Box becomes S squared ds squared plus S dr ds plus S squared R is equal to 0. And there are two linearly independent solutions to this second order equation. Typically, so when it's, all right, the notation they use, just like sine and cosine have the words sin and cos. Who were those people? Sin, cos? Were they like somebody's names or something? Like, I don't know, Sinbad and like, what, cosplay? I don't know who those two people were, but for some reason they call these y naught and j naught. Okay. Okay. Where this index denotes the order. Index denotes the order. Best order of the Bessel equation. And people use these so much they call these Bessel functions just functions of the first and second kind. Okay. J naught and Y naught. Okay. And they kind of look like this. That's what J naught looks like if this were the S axis. And Y naught would look like this. Oh, I can do better than that. Let's use a different color. Whoa, looks so good with different colors. I only figured out like half when this term is over. All right. Why not of S? Oh, that looks so good. All right. And if for some reason you want to know what these look like, but this is why we have the lookup tables, J alpha of X. Oh, what happened? Why isn't like, oh no. How did it get so thin?
You're running out of electronic ink.
Okay, in case you're wondering why we call it why we don't just write it out, I'll tell you what J alpha looks like. The mathematicians have told us it looks like the infinite sum of -1 to the m over m factorial gamma function of m plus alpha plus 1 times, that goes in the denominator, times x over 2 to the m plus alpha for m equals 0 to infinity. So that's why we're just going to call it J naught, because this does not really. This tells you how they tabulated it. I think they had some poor grad student from the medieval days actually try to calculate these out. They have those tables. Don might remember this, but when I was in grad school, well, of course we didn't use them. We used computers, but like they'd sell these books of tables of sines and cosines, and they'd have tables of like basically a Bessel's equation. How did they calculate all those tables when they didn't even have computers? By hand? No, it can't be by hand because there's just so many.
It was monks. Oh yeah. They did all the dirty work.
They must have had some really bad computer that like spit it out in like little like dots, and you had to someone tabulate it. But yeah, those. Yeah, now you can just look that up online. Oh shoot, we're running out of time. All right. Okay, so basically the solution for R is going to be basically some constant times J naught, and to redimensionalize again, not using our S variables, be Y naught of lambda R. Okay, so that's the dimensional, not the dimensional, but it's going back to our old notation. Note, Y naught unbounded. as s goes to infinity, s goes to 0, sorry. So if I had to draw this green thing like really accurately, it would basically go down because it basically goes to negative infinity. It goes negative infinity. But w is equal to t of t bar, r of r bar is bounded at r bar is equal to 0. That means that b is equal to 0. So we don't have that term. So that's applying one of the boundary conditions. So that means we have r of r bar is equal to a j naught of lambda r. All right, now this is where the fact that this lambda comes in, and we have to have sums of solutions. So the boundary condition, remember, boundary condition 1 is that w of 1 of t bar is equal to t of t bar. R of 1 is equal to 0. That's no slip. W. The second one, okay, no. So that one, we require R of 1 to be 0. Because the time-dependent part was exponential. That doesn't, only way it can be, that never goes to 0. So this t, capital T, never goes to 0. So that means the only possible way is R at 1 has to equal 0, which tells us that j naught of lambda has to equal 0. So this is what's called the eigenvalue condition. So that tells us which of those Bessel functions that we actually care about. So we're going to denote the 0. So I drew you the Bessel function. It kind of looks like oscillatory going towards the x-axis. Denote the 0 of the Bessel function by lambda n, okay? Because it hits the x-axis so many times, we're just going to denote them as lambda n, where n is going to go from 1, 2, 3, etc. So one of many solutions, we call that a particular solution of w is going to be called a sub n j naught of lambda n r bar times e to the negative lambda n squared t, where I'm substituting for my time-dependent part, the t. Okay. All right. So the most general solution is the sum of all those. Sum. All right. So the problem is I've introduced a new concept, capital A sub n. I got to get rid of that by using the initial condition, w of r bar 0 is equal to negative 1/4, 1 minus r bar squared. And that allows me to write this. All right, so this gives us equations that we're going to use the orthogonality probability of these eigenfunctions. that orthogonality probably says if I integrate between 0 and 1 of the product of r times j naught of lambda m r bar times j naught of lambda n r bar, that's going to equal 0 negative r if m is not equal to n and is equal to non-zero if m is equal to n. I'm sorry, we're over time, so I'll continue next time. But that's pretty much like what you need to know. So the office hours will be until 4. I'm just kind of busy at noon. You've probably done this orthogonality thing before with like the sines and cosines probably, but maybe not with this, but it's kind of like the same idea. Okay. What's up?
So like the shear stress and the time between velocity 0 to velocity steady state, it's just, it'll change just a lot faster in that period of time versus than the steady state time.
Well, it's basically, this physical problem is the tube is, there's no flow in it, and then I impose the pressure gradient, and I want to know what the flow looks like for all time. And I'm saying really, really infinite far in the future, it looks like the steady state solution. And we're trying to solve for W, which is basically everything until then.
But I'm just curious because for like the project, I'm worried about like the time between that steady state and what is that shear stress change.
Oh, well, once we solve for the velocity field, you can figure out the shear stress anywhere by taking du dr.
Right.
I mean, the solution looks like, a solution W looks like this, where you have this exponential function of time. And this tells you what it looks like from the wall. So, and that looks, from the wall, it kind of looks like this thing. It's going to be like, but it said only goes at wall equals r equals n. R equals n. So this is across S. So I'm guessing kind of like, the one we actually care about is going to be something like here. This is going to be S is equal to 1, I'm guessing. I don't remember what the scale is. But it's going to be all the solutions like in that space. You could probably just take the first 3 or something if you really wanted to calculate something like this.
Gotcha. Thank you.
Yeah.
Good.